Hello, this is a video on surface area and volume. This will be an introduction. Okay, the first thing I'd like to do is take a look at a few shapes. In our math resource office, we have these small relational solid set. So we have a cylinder here, for example, has two circular bases. Right here is a prism. This happens to be a hexagonal prism, has two parallel bases that are hexagons. This is a triangular prism. It has triangle bases and the other faces are rectangles. Here we have a sphere. We also have another set here that has larger ones, and these are kind of interesting because they also have some plastic in here that you can take out. So this is a square-based pyramid, what I would call maybe the Egyptian pyramid. We can take this bottom off, and we can pull this out and flatten out this net, and we can see that the pyramid, square-based pyramid, is made up of 4 triangles and a square. The hexagonal prism here, let's take this one apart. If we take this one apart, the part around the middle here can open up into a rectangle, and then the two bases are going to be hexagons. It might be interesting to think about the dimensions of this rectangular piece that's made up of a whole bunch of rectangles. The lateral faces of a prism are going to be rectangles. So here we have the cylinder. It also has parallel bases that happen to be circles. And here we have the cone. And this particular set has the cone and the cylinder having the same circular base. And if I take the plastic out of here, we can see here, if I flatten this out, that the curved portion opens up to a rectangle and the two bases are circles. Now we have a very interesting phenomenon going on with volume, and this can be demonstrated with these particular manipulatives. Here we have the cylinder, and here we have the cone, and if I put this cone in here, it turns out that this cone has exactly a volume 1/3 the volume of the cylinder. And what an excellent activity to do in class is to have some water with food coloring in it. Fill up your cone here with your colored water, pour it into the cylinder, and it should come up to about 1/3 of the way. Then you fill up your cone again, pour it in again. It should come up to about a 2/3 point, and fill up your cone a third time and pour it in, and it should fill this. And this shows that the cone has a volume of 1/3 the cylinder. This is also true of prisms and pyramids. The pyramid is going to be 1/3. And I've got one more example here that's kind of a nice one. Here's a cube, which is a rectangular solid. It is a prism, and this particular foldable is set up where it opens up and you can see the three pyramids that together make the prism. The next thing I'd like to do is look at our formula sheet. And this is what we call the Wisconsin Mathematics formula sheet. I found this online and I really like the way it's formatted. One of the things I'd like to point out right away is the way we use the term base. In a two-dimensional figure here, the triangle, area is 1/2 base times height. And this base refers to a length, and we use a lowercase b. Here in the case of the trapezoid, we have base 1 and base 2, which are the two parallel bases. So lowercase b on this sheet, and base stands for lengths. We can have a base of a parallelogram. On the other hand, when we get down here to a prism, and we want to find the volume of a prism, we're going to take base times height. But this base now is the area of the base, and we're going to be using the capital letter B. In a similar manner, the prism actually acts very similar to the cylinder. It's base times height, but it's the area of the base. And here we have the pyramid, 1/3 base times height, as I demonstrated with the manipulatives, and the cone is 1/3 base times height. And one of the things I like about this is they're very consistent here, 1/3 base times height, 1/3 base times height, and so on. The base might be a square, it might be a pentagon, whatever. You need to find the area of the base. And in the case of the cone, the area of the base is going to be the area of a circle, which we have up here, which is pi r squared. So this cap B here is pi r squared in the case of the cone. I also want to emphasize here that there is a page 2 to this, and this gives us the formula for finding the area of a regular polygon. In this particular case, it is a regular hexagon. Regular means equiangular and equilateral. And the area is 1/2 perimeter times apothem, or apothem. The apothem is this distance from the center point to the midpoint of a side. If we look at our handout on important terminology for surface area and volume, I have a link here for apothem. And this is kind of a nice little applet that gives you a chance to manipulate a little bit. And the definition is here. A line segment from the center of a regular polygon to the midpoint of a side. And it is going to be perpendicular by symmetry. And we could use congruent triangles here. So you can manipulate this a little bit here. You can also change the number of sides. You can have the apothem of a four-sided figure. It might not be very useful, but you certainly can do that. You can do the apothem of a triangle if you want. Here's the apothem of a hexagon. Now, one of the things to notice about a hexagon that's important here is that a hexagon can be thought of as 6 equilateral triangles. So if we draw in these radii, we get a nice equilateral triangle here, which is 60, 60, 60, and the apothem forms a 30, 60, 90 triangle on this side and a 30, 60, 90 triangle on this side. So this is our apothem. Now I'd like to do some examples. Example number 1. Find the volume and surface area of a pentagonal prism. The base edge is 12 centimeters. The apothem of the base is 16.5 centimeters. The height of the prism is 14 centimeters. Okay, so the base edge is going to be 12. That's down here. All of these are 12 because it's a regular pentagon. And the height is 14. Now, the area of the base, whether there's one base, as there is in a pyramid, or two bases in a prism, is very important. And it's a good idea to draw just the base. And this isn't a very good diagram here, but we'll try to do our best here. So we have 12 on each of the sides. And I'm going to draw in my apothem. My apothem here is 16.5. And so I need to calculate the area of the base. And I'm going to be using the capital letter B, just like on our handout, and I will consistently use that throughout the video. Our formula for the area of a regular polygon is 1/2 perimeter times apothem, which is going to be 1/2. Now we have to find the perimeter of the polygon here. Well, we have 5 sides. 5 times 12, that's 60. And the apothem here is 16.5. In the case of the pentagon, the apothem is going to need to be given to you. In the case of the hexagon, you will be able to figure it out yourself. If I multiply this on a calculator, I get 495. You might check that. Now I'm ready to calculate the volume. It's always a good idea when plugging into a formula is to write down the formula first. I found that we plug in more correctly if we have the formula in front of us on our paper. So if we look on our formula sheet, volume is base times height. This is going to be 495 times the height, which is 14. So I take this number that's still warm in my calculator and hit times 14, and I get 6,930. 6,930, and we want to make sure to put our units on here. This is going to be cubic centimeters because we're taking centimeters times centimeters times centimeters. Now let's calculate the surface area. If we look at our formula sheet, we see that the surface area is going to be the sum of the areas of all the faces. So the first thing I'm going to do is take 2 copies of the base, because a prism has 2 bases. And then my lateral faces are all rectangles. So I have 12 times 14, and I have 5 of those. So I'm going to have 5 times 12 times 14. And we can run this into a calculator, and we get 1,830. And our units are going to be square centimeters. Now let's go to our second example. In our second example, we're supposed to find the volume and surface area of a triangular prism. The base edge is 5, so we have 5 on each of these base edges, and the height is 6. Once again, we need to calculate the area of the base. So I'm going to draw the base here. It's an equilateral triangle, and the 3 sides are 5, and area of a triangle is 1/2 base times height. Which means I need the height of the triangle. So if I draw the height in here, I have 2 right triangles next to each other. In an equilateral triangle, the 3 angles are 60. So the left-hand side is 30, 60, 90, and the right-hand side is 30, 60, 90. And it's important to be able to flexibly use the relationships in a 30, 60, 90 triangle. To go from the hypotenuse to the short leg, you divide by 2, so we have 2.5 down here. And to go from the short leg to the long leg, we multiply by √3. You can also use the Pythagorean Theorem, but since this is so common, it's a good idea to just use the rule. So the area of our base here is going to be 1/2 times 5 times 2.5 times √3. And I think I'm going to go ahead and run this into a calculator and use the decimal form. It's important that I don't round off too much in the beginning here because I'm going to be using this in a subsequent calculation. Let's get this from a calculator. So this is the area of the base. Volume is base times height. So I'm going to have 6 times my base. So keep this number warm in your calculator. Do not clear it. Just hit times 6 and enter. And I get 64.9519. And now this is my last step. So I'm going to round off to 2 decimal places, 64.95, and put my units on here. This is going to be cubic feet. Now we need to calculate the surface area. So let's write down our formula. Surface area is going to be the 3 rectangles. The rectangles are 5 by 6. So we have 3 times 5 times 6 plus 2 copies of the base. Now in this case, I don't have the number warm in my calculator anymore, so I might either retype in the expression, but since I've got quite a few decimal places here, I should be okay. So I have 3 times 5 times 6 plus 2 times 10.825318, and I get 111.650636. And since this is my final answer, I'm going to round off to 111.65 square feet. Now we're ready to move to our third example. Before we go to our third example, I would like to talk a little bit more about the pyramid. A pyramid is going to have 3 heights. There's the kind of regular height, which is this center height here. It's with the yellow sticky on it. It's from the center of the base up to the apex. This is kind of the regular height. This height right here with the pink tab on it is the slant height. The slant height here is in fact on a slant, and it's on one of the faces. And the third type of height that you can have is the edge height. And this is the edge here that's going from a corner of the base up to the apex. These have been made out of coffee stirrers and pipe cleaners. So maybe I'll just pull this out of here. Here's the coffee stirrer, and here's the pipe cleaner. And I have a video on my website that tells how to make these, and it's a good activity to do with the students. It does take a while to build this, but they're learning a lot of math in building it. Next week, we're going to be studying a little bit more about the various right triangles that we have here and the various Pythagorean theorems, but we're going to just see one example tonight where we use the edge height here and the slant height to get a right triangle and use the Pythagorean theorem. So here is our third example. Find the surface area of a square-based pyramid. The base edge is 12, and the edges of the triangular faces are 10. So we have 10 here, 10 here, 10 here, and 10 on that dotted one in the back. And down here, I have 12 on each of the sides of the square. I won't label the dotted ones. So, as usual, we need to calculate the area of the base, and that's easy in this case. It's 12 squared, which is 144. And now I need to look at one of the lateral faces, the triangle. And once again, it's a good idea to pull this out. So we're going to have a triangle here. And I need to find the slant height. This is 10 on this side and 10 over here. And I have 12 along the bottom. And when I put the slant height in here, I am going to get two right triangles. Let me see if I can put the slant height over here as well. There we go, not too bad. Now, these two right triangles here are not going to be 30, 60, 90 triangles because we do not have a 60-degree angle, but we can use the Pythagorean theorem. So half of 12 is 6. And if I call this slant height L, and that's very typical, also on our Wisconsin formula sheet, I believe they use L. So I can set up the Pythagorean theorem. L squared plus 6 squared equals 10 squared. And I'll let you work that out. L squared plus 6 squared, or L squared plus 36 equals 100. Subtract 36 from both sides. I don't think I'm going to show all the steps here to save room on my paper. L squared equals 64. So the slant height is 8. Now, of course, in some cases it's going to be a square root, but this one comes out even. So now we're ready to find the surface area. So if we look at our formula sheet here for the pyramid, the surface area is the area of the base plus 1/2 PL, which is 1/2 times the perimeter of the base times the slant height. And it might be interesting to determine where that formula came from. So writing down our formula, we have the area of the base plus 1/2 PL. Area of the base we had is 144. The perimeter of the base. The perimeter of the base is going to be 4 times 12, which is 48. You can see that these problems require lots of mathematical thinking. both conceptual understanding and procedural understanding. And our slant height here is 8. And we're going to run this all into a calculator. 144 plus 192 is 336. And this is surface area, which is going to be an area unit. So we have square centimeters. I hope you have found this video helpful. Have a great day.